Okay. All right. Matt, the stage is yours.
Okay, thanks a lot, Soner, for the invitation, and hi, everyone. So now you can see everything, right? My pointer and like, okay.
Yeah.
Okay, cool. So the title of my talk is Virasoro Conformal Bootstrap with C greater than 1. And I'm joining you from Amsterdam. Slightly bad that we cannot meet in person, but yeah, it's still great that we can meet here over Zoom. So yeah, as Soner mentioned earlier, just please interrupt me like any moment. I mean, I have slides, but I don't have to finish all of them. I mean, we can just like talk about any questions you might have in between. So I'll start with just like a brief overview summary of Conformal Bootstrap in some words, and then I'll actually go to some basics and introduce conformal field theories, and then I'll move on to two-dimensional conformal field theories and discuss the bounds. Yeah, that will be the plan. So first of all, so the conformal bootstrap is something that you might have heard of in the recent like 10 years or so. This actually originated in the study of like two-dimensional conformal field theories. So the two-dimensional conformal field theories are special because they have an infinite dimensional symmetry algebra, which is the Virasoro algebra. And in the work of Belevin, Polyakov, Zamolodchikov, minimal models were discovered using conformal bootstrap. So that was a big success. So this minimal discovery of the minimal models used special discrete features of C smaller than 1. C is the central charge of the 2D CFT. C smaller than 1 unitary representations of the Virasoro algebra. So in this regime, there exist null vectors in Verma modules, and those null vectors imply differential equations for correlators, and this greatly simplifies the correlators and Virasoro blocks, and this leads to closed form expressions for both the correlators and Virasoro blocks. So for C greater than 1, unitarity says little. The only constraint from the Koch determinant computation seems to be that the dimensions of the operators, which I'll define actually in the next slide, has to be greater than 0. But other than that, there doesn't seem any specific simplifying features. I mean, the reason the situation is like difficult for C greater than 1 is Virasoro blocks are only known in expansions. So there is no closed form expression for these building blocks of correlators, and these expansions exist in various forms of the cross ratio. So the question I want to ask in this talk is, can we use Virasoro blocks to restrict the operator product expansion, which I'll also define in a moment, of a certain operator, and by way of that, the spectrum of a theory. So in other words, is there a correlator bootstrap with Virasoro blocks? And I'll try to convince you that the answer is yes. And we will use the cross ratio expansion of Virasoro blocks in a special setting where the coefficients are positive, and we'll use those positivity properties. So okay, so that was like a very broad overview, and I'll go into the details of conformal field theories, and I'll start with conformal field theories in general dimensions. So yeah, if you have any questions about the outline, just at any time ask me. So you might know conformal field theories are ubiquitous in physics. The reason for that is they define universality classes of quantum field theories, and the way that happens is they are actually fixed points on renormalization group flows. That implies that they have scale symmetry. So the usual Poincare symmetry of quantum field theories. On top of that, we have scale symmetries, and in 2 dimensions, you can show that Poincare symmetry combined with scale symmetry actually implies conformal symmetries, and in also higher dimensions, in many situations, that this is the case. So what do I mean by scale symmetry? By that I mean on top of your momenta, which I denote by P here, and the Lorentz generators, which I denote by J mu here, you have this extra scale charge D, and it's commutated with the momenta, gives back the momenta. And there's also something called a special conformal generator. That's also a symmetry in the theories that we'll focus on. And this basically lowers the scale dimension by 1 because of this minus sign here. And in the commutator of the momenta and special conformal generators, you have the usual Lorentz generators, and also the scale charge appears here. So we want to use these charges to restrict the form of correlators. To do that, the first step is to find out the action of the scale charge on a local operator. So that is, as usual, given by the commutator of the charge with some local operator that defines the action of our generator on a local operator like O of x here. So if for momenta, for example, this would be, P commutator O of x would just be the derivative. So in the case of the scale charge, this is the form you get. There appears a number here, delta, and that is called the scaling dimension of a local operator. So in conformal field theories, the vacuum is invariant under scale symmetry. That means when you act with the scale charge on the vacuum, you'll get 0. And what that means is you can just like write down your favorite correlator, endpoint correlator of scalar operators, the vacuum expectation value. And the commutator of D with this whole thing is by this definition is just the sum of the action of the scale charge, which is this differential operator here, over all of these things. So since D, when it acts on the vacuum, it's 0, the left-hand side is 0. So the implication for correlators is this sum has to be 0. And the idea is to actually solve this equation and see what we get. And so on top of this, as I was saying, there's also this special conformal charge, and that also, because it's a symmetry, it annihilates the vacuum. So combined with the previous slide, this fixes the form of 2 and 3-point functions. So basically, if O1 has scaling dimension delta 1, by that I mean the delta that is appearing here, the 2-point function of any operator, O1 and O2, will only be non-zero if O1 and O2 are identical. So only identical operators have a non-vanishing 2-point function, and the scale dimension appears here. So this you can see, this is, you can think of like a mass dimension, and here you see that in the denominator because we have some length. So x1 to this notation means x1 minus x2. That is the shorthand for that. It also, the same invariance under Poincaré and scale and special conformal charges, it also fixes the form of 3-point functions. And this is what you get after solving this differential equation here for the 3-point case. What the symmetry does not fix is this coefficient here. So there's an arbitrary coefficient here, not fixed by conformal symmetry. So on top of these properties, there is something called an operator product expansion. And due to conformal symmetry, this operator products expansion, which I'll abbreviate as OPE, is convergent. So this is the OPE here. If you have some local operator, in a free theory, you could think of that just like the polynomials of the scalar field or so on. But in general, for general CFTs, they are just abstract local operators. And when you multiply these two things, these are operators. On the right-hand side, you'll have in principle, entire spectrum appearing. These OK. There is a sum over K here, or a sum over the entire spectrum of the theory, all the operators that appear in your theory. And this factor here, the x minus y raised to these dimensions, is fixing the scale symmetry of the correlators in which these guys will appear. And you also have some differential operator acting on these O's, and this differential operator actually sums up the entire conformal family of this operator. Okay, so I didn't say what it was, but the fact that the fact that d with p gives p and d with k gives minus k allows us to define a conformal family which is annihilated by k, and by acting with p as a raising operator, we can just start from a primary state defined by of 0 acting on the vacuum, and we can act with p and multiple times and along with its tensor contractions, and that will give us the entire conformal family. And this differential operator here is just summarizing that, and the sum here is over primary operators which are annihilated by the special conformal charges. So given the fact that this OPE here is convergent under certain conditions, that means you can actually, if you want to compute a 4-point function, 5, 6-point function, you can just use this expansion, this convergent expansion in your correlators, and that is going to tell you what the correlator is in terms of only these numbers delta k, delta I, which are the dimensions which appear here, and also Cijks, which is what appears. So this Cijk here has the first term in the sum is this Cij, this 3-point coefficient here. So the set, the dimensions and the OP coefficients, or the 3-point coefficients, fix the entire correlators, all correlators of your theory. And that gives us a way of just attacking this problem as a bootstrap problem, which I'll talk about next. So the first thing that is not fixed by conformal symmetry.
Can I ask a question?
Yeah.
Well, if the two different operators are at the same position, then we can't use this OPE.
Yeah, true. So this OPE tells you how the approach is described. It is described by this guy here. So we are interested in correlators at non-coincident points, basically, and that's what I mean by correlators. There will be, so if you're in an Euclidean CFT, but I mean there's a singularity. I think that's what you're pointing out. There's a singularity, but we know what the singularity is like. It's precisely this. But if you go to Lorentzian, there will be light cones and commutators and so on, which is slightly more complicated. But in this talk, I'm focused on Euclidean conformal field theories.
I got one more question about the same equation. At the end, there is a OK.
Mm-hmm.
I mean, is that operator supposed to be same operator at the left ones?
No, there is a sum over k, so all of your local operators will appear on the right hand side in principle, if it is allowed by the symmetry considerations.
So so this can be the operator of the algebra.
So it will be, so we're basically defining a CFT as a set of operators. Each has a dimension, and all of those operators will appear on the right hand side in principle. For any two starting point of your OPE.
I understand. Thank you.
Okay, so the first thing not fixed by conformal symmetry is the 4-point function, and again we try to make the most of our equation here, and the corresponding one with the special conformal generator here. What this equation tells us in the case of the 4-point function is basically it tells us there will be, so if you are at Euclidean points 1, 2, 3, 4, there will be this combination here. Again, this is x1 minus x2 raised to some scaling power, and there will be an arbitrary function in the numerator, the arbitrary function of cross ratios. Cross ratios are u and v defined in terms of these x1, x3, x4, like this. As you can see, when you act with the scaling dimension on the differential representation of the scaling charge, it just leaves it invariant. You will get 0. So an arbitrary function of u and v can appear. That is, so that g is not fixed by conformal symmetry. So so the idea then is to use the OPE. So now I'm just focusing on identical scalar operators, which I called phi. This is an example of OIs we had in the previous slide. Using the OP inside the correlator, let's say we do this S-channel OPE, which means we are using these cross ratios U and V here. So we basically take the OPE between this guy and this guy, and we use another OPE between this guy and that guy, and basically plug in this expression here and use the known form of this differential function, and basically we get this equation. So remember, there will be a Cijk from each OPE, and there are two OPs we are using here. So we'll basically have C phi phi O squared summed over all the local operators in your theory. And yeah.
I'm sorry to disturb you. Maybe you should mention that this C and the other C are different. Like you use the same letter for both OP coefficients and the differential operator C.
Exactly. Yeah, you're right. So I should have done that. So, but my logic was when I'm using like arguments, this is a function. But yeah, when I'm not using argument, it's a number. But you're right. This is actually a differential operator, and the first term. So this will have arbitrary powers of this partial derivative on y, and the first term is literally this number, and the next term will be y del y, and the next term will be all of it will be multiplied by this number here. But yeah, you're right. Thanks. Is that clear, or yeah? I haven't written as clearly.
No, I think it's clear. I just thought it would be better to say it again.
Cool. Yeah. So now these numbers C squared that appear here are actually literally these 3-point coefficients now, and we basically absorb all of this the differential action on these O's into these what are called conformal blocks. So basically we did this OP here and there, and we were left with O here and O there, and we replaced that with the 2-point function and acted with the differential operator that gave us this conformal block. So yeah, these conformal blocks are known explicitly in even dimensions, and there's a way to compute them, which I'm not going to go into because I'm not going to use it. You can basically write down this conformal Casimir equation, which is using the same ideas that we've been talking about. And you can actually write down an equation for them in any dimension, but you can solve those equations in closed form only in even dimensions. And there is a useful parameterization in terms of U and V. You can use what are called these Z and Z bars, which is basically just using conformal symmetry to take these 4 points to a common plane. You can do that, and Z and Z bar will be complex coordinates on that plane, and that's how you relate them to U and V like this. And in 2 dimensions, for example, they're as simple as this in terms of the Z variable. They're basically hypergeometric functions. You see the Z and Z bar, and it's symmetric under the exchange of Z and Z bar, and this is the expression in 2D. This is what is called a global block in 2-dimensional conformal. These are not the Virasoro blocks, which I'll get to next. So just using global conformal symmetry, which is just the D's and K's and the P's and J's that we just mentioned, you can fix the form of this guy in terms of hypergeometric functions. So we're still in general dimensions. And we're coming to the crux of the conformal bootstrap. So remember, we expressed this function, this 4-point function, in terms of this C squares and conformal blocks. But then we have written this equation using the S-channel OP, which was x1 and x2. merge into one, and x3 and x4 merge into one. But we are in the Euclidean regime, everything commutes, so we can move this around, and we could just do the OP between 1 and 3 and 2 and 4. But that's just like using the same, I'm sorry about that, using the same idea, but now in the T channel, you should get the same result, right? So that means we can write down an equation that using the S channel OPE minus the T channel OP, which should just give us 0. So basically, when you do the T channel OPE, 1 with 3 and 2 and 4, that basically changes the roles of U and V, and we get this GVU. And because these two expansions are the same, this should give us 0. So this now is a constraint on the spectrum of the OPE. So not everything goes. So your C's and dimensions of O's that are in your theory should be such that they satisfy this equation. And we just define this crossing function f here, which is just this difference here, and I'm rewriting this equation like that. So the spectrum needs to satisfy this equation for all values of U and V. And this is highly non-trivial. This is an you can think of these f functions, crossing functions, as infinite dimensional vectors, and to be able to extract some useful information from them, you need to project them onto a finite dimensional subspace. So the idea then is to just like take this equation and act on it with some linear functional alpha, which will set basically, we'll see some examples of it, which will set this U and V to some specific values, U to 1 over 2, V to 1 over 3, whatever. And then since it has to be satisfied for all values of U and V, it will have to be satisfied for your choice of alpha and U and V. It just has to be a linear functional. So then once you have like a candidate simple or complicated linear functional alpha, the idea is to find a contradiction. So now that we have a finite dimensional vector alpha here, we'll just plot the action of alpha on various values of O here. O has dimension delta and L. So you're seeing this alpha vector, its action on, let's say, operator 1, O1. Its action on operator 2 is alpha 2. On alpha 3, it's a different vector. So if the situation is somehow like this, these vectors on O1, O2, O3, O4 if they can add up to 0, like I suggest here, then there's a chance of satisfying this equation. But the idea is to find a contradiction, as I was saying. So if you can find an alpha such that all of the operators that satisfy unitarity bounds lie to one side of some plane, which we should call a separating plane. If the situation is something like this, these guys can never add up to 0, right? So that means your proposed spectrum cannot satisfy crossing symmetry, so it cannot exist as a consistent conformal field theory. So that is the idea. Are there any questions at this point? Cool. So let me just then reiterate what I was saying. So this is the Bootstrap algorithm, which was pioneered by these authors here in 2008. So the idea is to make a hypothesis about the spectrum of your operators. We were talking about phi with phi. And let's say so in the OPE, there will always be the identity operator. This one is standing for that. And there will be other operators, right? So let's say we want to make an assumption about the first excited states. By that I mean the lowest dimension operator above vacuum, which is the identity. And let's say we make an assumption about it, and then we're going to look for a linear functional alpha that is non-negative on all the operators in the OPE and strictly positive on the identity. So if we're gonna try to cook up this linear functional alpha such that in all the operators that can possibly appear in the OPE, it's non-negative, but on identity it's strictly positive definite. So what does that mean? That means this equation cannot be satisfied. It was non-negative on everything that it can appear here, but on identity, which has to appear there, it is strictly positive. So you will have had you will have created the situation here, and then you will have shown that this crossing equation cannot be satisfied. So then your hypothesis about O1 is wrong, and that is a way of just erasing out regions in theory space. Let's say if you assume this the dimension of the excited state operator, if you assume it is too large, if it is like much larger than, let's say, 4, if you're in 4 dimensions, you'll see that you can find this alpha that satisfies these things, and then you will have shown that such an operator, such a situation cannot be the case. The first excited state cannot have a dimension that is too large, for example. That is the general idea. And now I'll give an example of this. In the case of the 2-dimensional Ising CFT, which is a specific CFT that is the universality class of your usual 2-dimensional Ising spin chain, and the BPZ have shown that they have computed correlators of these things fully using the infinite dimension Virasoro symmetry. But now we have to just show the ideology. We're just gonna think in terms of global blocks, which we had shown that for the global blocks, the conformal blocks are just like these hypergeometric functions, and just takes as your external operator the spin operator that has dimension 1/8, and pick the specific cooked up linear functional alpha, which is 2-dimensional. This is the x coordinate, this is the y coordinate. These are some vectors, as I was mentioning, and use the specific function here, h, as defined like here, and then just look at the action of this alpha operator on your crossing function, just like we were supposed to do, right? This crossing function here. So it's basically telling you to plug in these real numbers here, and just look at the action of it on all of the operators that can possibly appear in your OPE. And here I'm showing you, and try to satisfy this equation. Here I'm showing you some plot from David Simmons-Duffin's TASI lecture notes on the Conformal Bootstrap. If we just plot this 2-dimensional linear functional here on the unit operator, which has dimension 0, you'll see it will just give you 0. And then here we see these dots represent all the symmetric traceless tensors that can appear in the OPE of identical scalars, and these numbers denote the spins of them. So here we see the stress tensor, which has dimension 2, and I didn't mention this, but there exists unitarity bounds that tell us the dimension of a certain operator of a given spin cannot be too small. So there is a minimum dimension you can have for each spin, and this dot represents that. Start from that. Let's say we are at spin 4, and then just look at the action of alpha as you keep increasing delta. So any dimension above this dot, so along this trajectory, is in principle allowed in the spectrum. So when you keep increasing the dimension up to infinity, you can see that the action of this guy, this 2-dimensional vector, will just trace this green trajectory here. For dimension 6, you will get this trajectory here. This is the delta goes to infinity limit. And for all of your possible operators, these are the curves you'll get. But if you look at the scalar operator, which is the first excited state you can have in this 4-point correlator of identical scalars, this alpha functional traces out a curve like this. So we now looking at this picture can identify a separating plane, just like the thing that I was showing you here. And if you identify a separating plane, that means that spectrum is ruled out, right? So here, this is our separating plane, and if all your operators are on this side of the separating plane, you can never satisfy this equation. That means, so this is a thickened version of this thickened part of the curve has to be in your spectrum. If your first excited scalar primary in the OPE of this guy here has dimension lying on the right hand side of this guy, you cannot satisfy this equation, so it has to lie here. So the conclusion here is there has to be a scalar with dimension in between this range. This is computed just by, these numbers are computed just by looking at this linear functional here. And here we got some useful information right now, right? So there has to be a scalar with dimension that is between these values. So this is one example, and this was just like, this was a cooked up linear functional, and we're going to try to generalize that, and that will be the rest of the talk. So this is actually, in this case, we knew the result using the infinite dimensional Virasoro symmetry, and the first excited state has dimension 1. So this is pretty good because it's saying its dimension cannot be greater than 1 or 4. So yeah. But yeah, we already knew the answer in this case. In cases where we don't, Bootstrap is powerful and useful. Any questions up to now about the methodology? Okay, let me check. Okay, this is, I'm not doing amazing on time. So I'm just gonna flash to you what is a more general case. Here I was showing a specific example here. A more general thing to do is just act on your crossing function with derivatives and set them to some specific values of the cross ratio. A useful point is in the cross ratio space is the crossing symmetric point here. And in b equals 3, for example, in odd dimensions, we actually don't know we don't have a closed form expression for conformal blocks. We only know them in a recursive expansion, and the specific linear functional example I'm showing you has this nice property that it is something positive multiplied by some polynomial here. And one then absorbs this positive function into the OP coefficients, which appear in squares, so they're positive, and work with these polynomials. So we're going to do something similar with Virasoro blocks. This brings me to the two-dimensional CFTs. Two-dimensional CFTs, as I mentioned, have local conformal symmetry. So on top of the finite dimensional conformal algebra, we mentioned the momenta, Lorentz generators, and the scale charge and special conformal charge. It has actually an infinite collection of generators that satisfy this Virasoro algebra. Using these Virasoro generators, you can actually cook up what are called KdV charges, and they will be like literal conserved charges. They will commute with the Hamiltonian and so on. But the basic building blocks are these infinite dimensional, the infinitely many Virasoro generators. So this M and N can be any arbitrary integer here, and they satisfy this algebra. So among these Virasoro generators, there is a Hamiltonian on the cylinder. Hamiltonian on the cylinder will be L0 plus L0 bar. So, okay, there's actually two copies of the Virasoro algebra. The second copy is delineated by this bar here. And a representation of the Virasoro algebra is specified by two numbers, the central charge and the dimension h. This h is basically the eigenvalue of L0, the Hamiltonian. It's the energy on the cylinder. So this very brief review of to the CFT symmetry algebra, and next we go on to our objects of interest, which are correlation functions. The 2 and 3 point functions are just the same as before. They are fixed. And they have the same form as in higher dimensions. And the 4-point correlator is not fixed by symmetry. And here I'm looking at a specific, so I'm using conformal symmetry, I can just like move 3 of these guys to to my desired locations, the origin of the plane, of the 2D plane, to point 1 and infinity. And the only thing unfixed will be these the position of the second operator at C and Z bar. So this is the 4-point correlator. And again, we decompose it into building blocks, but now into Virasoro blocks. So we want to use this infinite dimension Virasoro symmetry and decompose it not in terms of the global blocks, which were just the hypergeometric functions, but into this full Virasoro block. So this thing will not satisfy a Casimir equation, but you can act with your Virasoro generators. And I'm not showing you here, but you can actually derive the action of this LM on a local operator, just like the scale charge acted like in the higher dimensional case. Using the action of these LMs on the local operators, you can show that these Virasoro blocks actually have a series expansion in Z. So if we are using the S-channel OP, that means we are looking at Z going to 0. So as Z goes to 0, this Virasoro block will have a power series expansion in terms of C. This will go like Z squared, Z cubed, and so on. So the bad thing is just like odd dimensional CFTs, in 2D global blocks are known, but the Virasoro blocks, there exists no closed form expression for these guys. So we cannot use this FUV here. The hypergeometric, we were using the hypergeometric function form to deduce this curve, right? We were actually explicitly computing this curve using these hypergeometric functions here, but now we don't have that. So we cannot trace something like that and look for separating planes and so on. So we'll have to do something more creative. And Zamolodchikov, if you're looking for creativity, Zamolodchikov is the answer. So he actually related this plane block to a new function. This is at this point ad hoc. And I'm just flashing to you the formula here. And you see we now define this, what is called this elliptic norm. Z was our coordinate on the plane, and it was also the cross ratio. And he related this Z to this tau here. And using this tau, he defined the elliptic norm. And just like for us right now, ad hoc rewrote this plane block in terms of what I'm going to call the Zamolodchikov H function. And using actually the minimal models and unitarity and so on, he wrote down a recursion relation for this H function. He actually wrote down a recursion relation for both this plane block, which gives you these coefficients of Z's here, but he also, using that and this definition, wrote down the recursion relation that gives the coefficients of the Q expansion of this H function here. So the first time this function, this Q, this H appeared is kind of like complicated. It goes back to a paper of Zamolodchikov on the Ashken-Taylor model, and which is a specific CFT with central charge 1. And he reframed the conformal block, the differential equation for the conformal block as an eigenvalue problem. And when he was trying to solve the eigenvalue problem, he encountered some of these elliptic functions, like this is the elliptic theta and so on, and that is how it appeared. So it was kind of like an ad hoc definition until Maldacena, Simmons-Duffin, and Ghiboirov gave an interpretation of this. So to go to understand that interpretation, so that relies on what is called the pillow quantization. Before going into that, I will just mention that this plane block decomposition has a radius of convergence 1 in Z on the Z plane. So this domain of analyticity can be extended to the entire Z plane minus a cut. But the full domain of analyticity is actually much larger because the Q expansion, the thing that I showed you here, it actually converges on the unit Q disk, which contains as a sliver here the entire Z plane. So the plane block expansion converges on the sliver here, but the full domain of analyticity is this entire Q plane. So a Q expansion of a 4-point correlator or any bootstrap algorithm, depending on the Q expansion, it will be much more powerful in constraining the spectrum than the Z expansion. And yeah, let's just mention how this comes about. Okay, I'm not gonna go into the details of this, but to what Zhiberdov, Maldacena, Siemens-Duffin did was express the 4-punctured sphere, which is our object of interest, since you're looking at a 4-point function on the sphere. That can be expressed as a torus modeled by Z2, which we'll call the pillow torus, and there is a conformal map from this pillow torus to the 4-function sphere, and using that map and using conformal symmetry, that relates your 4-point correlator to something, some correlator on the pillow on the pillow geometry, which I'll show you here. It'll be in the next slide. And these authors gave an explanation to all those weird-looking like elliptic thetas and so on appearing in Zamological's ad hoc-looking definition. So let's just take this as a definition at this point and just observe what the crossing equation becomes. So the crossing equation for us was basically relating the S-channel expansion to the T-channel expansion. So the S-channel, in the T-channel expansion, Z is mapped to 1 minus C, Z bar is mapped to 1 minus C bar. And this is our crossing equation. And if you look at the definition here, like K, this is the elliptic K function, 1 minus Z in top and Z at the bottom. This basically, if you map Z to 1 minus C, you basically take this tau to 1 over tau. So this map from Z to 1 minus C here appears as tau to actually minus 1 over tau, and tau bar to minus 1 over tau bar. So we have rephrased our crossing equation for the 4-point correlator, the plane correlator F, to an equation for the pillow correlator in terms of Q like this. So these are identical now. These contain the same information, but if you expand this guy in plane blocks and this guy in pillow blocks, this will any information you try to gather from those expansions using some bootstrap algorithm, this guy will be more powerful because, as I was telling you, the Q expansion has a much larger radius of convergence. So, well, of course, if you expand this guy in terms of Q, it will have the same power, but this is more natural to expand in terms of Q because it's just it's the Q variable, which is e to the I pi tau that is appearing naturally in this equation. So our new crossing equation is this guy. So this map, as I was saying, contextualizes Zamological's Q expansion, and it further lets us identify the pillow blocks. So just using this map here, the holomorphic part of it, if this guy, the pillow correlator, has an expansion pillow blocks, it will have lambda to the minus 1 multiplying your plane blocks, right? So here I'm just writing that. I'm defining pillow blocks. They're the same as your plane blocks multiplied by this lambda function. And if you use Zamological's definition of the plane block that related it in an ad hoc way to its H function, you get a map between the pillow block and the Zamological H function here. You have this Q here appearing here and this Dedekind eta function, all coming from this conformal map from the sphere to the pillow. So the good thing here is now we have a torus. So if you have a torus, then you can prepare states on a spatial cycle here, and then interpret the correlator as the action of some propagator along the torus. And then you can write down this pillow block and the pillow correlator as some norm. So the states are created by, so this is the pillow, you see the four, it's just like a 4-punctured sphere, like expanded into a pillow. So the states created by the two of your operators propagated by this guy, by the Hamiltonian here on the torus, and taking the inner product with the bra version of it, you just get the pillow block. So what is good about this thing? This was just an interpretation, but what it's telling us that this guy is actually a norm. It's a norm in the pillow quantization of the 2D CFT. So what is a norm? What is good about a norm? It's positive. So before when Zamolodchikov had defined this function, it was not obvious that he had given a Q expansion, but the expansion coefficients could be arbitrary numbers, arbitrary real numbers. But now we know, thanks to this interpretation of pillow quantization, we know that they have to be positive numbers. And we like positive numbers because if something has an expansion in terms of positive numbers, we can use that to constrain the terms in the sum, right? They cannot be too large, otherwise the thing will never add up to 0, your crossing function. So here is another technical slide, but I'm just gonna just skip it fast. So this I'm just actually writing down the Zamolodchikov recursion relation here. This he just gave how to expand this H function here in terms of powers of Q, and yeah, we don't need anything more than here. This just I'm just using some notation from these authors here. All this does is give a Q expansion for the H function. And for identical operators, odd powers of Q are absent. So the pillow correlator, as we have seen, now admits an expansion in terms of pillow blocks. And we related the pillow blocks to the Zamolodchikov H function. And I didn't explain it, but I told you that this H function has an even power expansion in terms of Q. So if this guy has an expansion, power series expansion in Q, that means this guy will also have, you can relate using these functions, Dedekind's, etas, and so on. It will have a Q expansion, not in integer powers of Q, but because of these powers here, it will have this H minus C over 24 and times some integer thing, and there will be some coefficients. And what we have seen due to the pillow quantization is these A guys, these coefficients have to be positive. So if we can just like use all of these information and write down a Q expansion for the pillow correlator, it will have these OP coefficients, and it will have, so there's a sum over all of the operators in your theory, Virasoro primaries, and for each primary you have a pillow block. And now I'm writing the pillow block twice because there is a holomorphic part and the anti-holomorphic part. So we have a nice expansion of the correlator in terms of positive numbers here. This C squared is positive because it's C squared. These C's have to be real, and we have just seen these A's are positive, so we have a nice positive expansion. So the strategy is to compute a fixed number of expansion coefficients for the H function using this technology here, and then plug the resulting series in this guy here, and then get some expansion of the pillow correlator itself. So I'll just give an example of these this Q expansion in the well-known case of the Ising CFT, which is just a C equals to 1/2 CFT, and one of the operators in the spectrum is this spin operator, which has holomorphic dimensions 1/16, and since this is a minimal model, the correlator is known exactly, and it has been decomposed in terms of plane correlators exactly, and this is the expression for these Virasoro blocks, which have very simple expression like this. You can just plug this into the definitions. So remember this plane block appeared here, and it's related to the H function like that. If you plug that in, you can get an expansion of the H function here. And here we are seeing the pillow positivity property at work. If you just expand the H function, you'll have this arbitrary expansion, again with even powers, but negative and positive and negative arbitrary sign expansion. But if you look at the specific combination here, which was just this combination here, we were claiming due to pillow it's positive, and we are here seeing it at work. It's literally all of the terms you can convince yourself are positive. Actually, you can convince them, all of them positive, because here we have the closed form expression. So this is the property we want to use, not for minimal model, but for generic C greater than 1 conformal field theories. So we're continuing with the pillow expansion, and we're focusing on a rectangular pillow torus, and we're parameterizing the torus with these I beta, and tau bar will be minus I beta. I have some more definitions here. This is the pillow correlator. Here you see the identity block, the contribution of the identity operator. It's not just a 2-point function, because the identity block has all of the polynomials, multiples of the stress tensor, so it's an infinite expansion, just like the first excited state. So now I'm using a new definition. I'm just like shortening, instead of writing C 5 phi 1 denoting the first excited state, I'm shortening that to C1 squared. So this is the usual 3-point coefficient, and this is the first excited state, and just literally plugging in this, like tau being I beta over pi, and Q, remember, was e to the I beta tau, and using that you get this like expansion in terms of exponentials. And if you want to remember how this beta is related to the crossing functions, you need to remember this definition here. So tau is related to the cross ratio Z like that, and tau is also related to beta like that, so that there is a precise map between beta and Z. So this beta is actually not a temperature. We are on the pillow torus, and this beta is just like is the cross ratio. And here I showed the first term in the expansion, first non-trivial term in the expansion. And you can compute this guy using the recursion relations that I showed you. It's this complicated looking thing. And this delta O is the dimension of the external operator, central charge appears here, and the dimension of the exchanged operator. And so the good thing is, like, I was claiming this has to be positive, right? You can just look at this complicated looking thing, and by inspection, you can see that the denominator is positive for C greater than 1 and all real H. That's what I want. That's we wanted. The numerator is positive for a larger region, C greater than 0, H greater than 0, and delta O, the external operator, greater than 0. This is a positive thing. This was guaranteed to be positive by pillow condensation, and now we are here seeing the example of that. So what are we going to do with this positive expansion? I'm rewriting this crossing equation. This was the plane version of it. This was the pillow version of it. We are parameterizing the torus in terms of parameter P here. Tau was related to Z like that, and calling this I times e to the P. And we can compute to tau bar. It will just be minus I e to the P. And corresponding values of 1 over tau and 1 over tau bar are just easy to compute like this. We needed to compute them because they appear on the right hand side. And we are interested in an expansion around the crossing symmetric point. Crossing symmetric point, in terms of the plane cross ratios, was Z equals to 1/2. In terms of the pillow coordinates, it's tau equal to I. And in this parameterization, it's P equal to 0. All these definitions are actually to, again, rewrite this now pillow version of the crossing equation in terms of P like this. I'm just writing this equation, just substituting tau is equal to I e to the P. And this is the thing. And remember, this is satisfied for all real values, so all real values of P. And in terms of beta, this so the idea is actually I'm taking the idea from Hellerman. He used this for the actual torus and a finite temperature CFT. Since this is satisfied for all values of P, we can differentiate this equation with respect to P and set P to 0 at the end. And this is the functional that is doing that, taking m derivatives with respect to P of both sides and setting P to 0. What does setting P to 0 mean for beta? It means setting beta to 2 pi. So basically, this is the left-hand side. This is the right-hand side. Then this is the left-hand side. And basically, I'm just like differentiating with P and setting P to 0. And this is the equation that are correlated has to satisfy. That is the crossing relation. So for each m, since we are setting beta to pi, and remember beta was appearing like this here, e to the minus beta e was the dimension, related dimension like that. We get some transcendental equations, some exponentials of the dimensions. So we get a equation involving exponentials of the spectra. And I'll denote the contribution of each conformal family by these IMs here, and acting on a term like this, and the next term in the expansion we will have these recursion expansion coefficients and so on. And here I'm writing this functional which I'm denoting I1. It's just like one derivative with respect to P and then setting P to 0, which meant beta equal to pi. So this is what we get. We see here the central charge, the external dimension, and the internal dimension. Remember, E was the internal dimension, combination with the C central charge like this. I3 is more complicated. It is like this. And the crossing equation just becomes the identity block should be the contribution identity block is balanced by the entire spectrum of the theory like this. Okay, this will be hopefully clearer here because now I'm going to simplify. So these functionals are complicated for generic central charge and external dimension, but you might see here if you set C to 16 delta O, these things simplify quite a bit, and they take this form here. So that's why we'll study the special case of C equals 16 delta O, since the equations are easier to the I. And this is the one derivative equation. This is the 3 derivative equation. And the sum is over the all of the operators in your theory. So this K prime denotes all of the operators, not just Virasoro primaries, but all of their descendants, their global descendants. So these are all, these are called quasi-primaries. The sum is over all quasi-primaries. But we can, since we are interested in restricting the spectrum in terms of primaries, we can express this as the primary contribution and the first term from the Virasoro block expansion like this. This is the I1, this is the I3. The highlight here is the first term in the expansion of the Virasoro block is actually larger than the second one, because you see the second term is suppressed by e to the minus pi times 2, right? So we can basically, as a first approximation, neglect these guys. And observing as I was saying, the relative separation of higher order terms, which by this e to the minus 2 pi, which is a small number, we truncate to the first term, and now we have the same exact equation, but it's now over Virasoro primaries. And expressing the energies in terms of dimensions, and after substituting the first equation into the second one several times, we get these equations. So the first and second equation become this and that. Now we have this nice equations for the spectrum. Let's see. So this f of delta is just this function, 12 delta minus c. G of delta is another polynomial. So yeah, we ended up through all this machinery, pillow quantization, recursion expansion, and so on. We ended up in these two equations. Our spectrum has to satisfy that. These are just some positive numbers. 3-point coefficients, and these are the polynomials that you see here. And yeah, this is this will be non-trivial to satisfy, and we're going to see how we can restrict the spectrum using these guys here. So the functions f and g have the nice property that they are positive above some threshold value of delta. So you see f is positive if delta is greater than c over 12, and g is positive for delta greater than delta bound, which is c over 6 plus 3 over pi, which is greater than c over 12. So so now we're ready to make an assumption on the spectrum and show that it is false. So we're going to assume the first excited state has dimension delta 1, the 1 denotes the first excited stateness of it, greater than this delta bound. Then what do we end up with? We end up with this set of inequalities here. So basically, this inequality holds because we are assuming this is the first excited state, and all of the states above this have dimension greater than delta 1. So this sum with g inside the sum will be greater than with g factored out and set to the value of the first excited state, right? So all of these delta k's are greater than delta 1. That is the assumption. That means g is greater for all of them. So this sum on the right-hand side is greater than the second sum. But this right-hand side sum is actually 0. That was our crossing equation. That was the second equation here. So on the right-hand side, we have 0. On the left-hand side, we have this g of delta 1 multiplying this sum here. But remember, this sum was actually the first equation, which just happened to be c times e to the minus e0, the first excited state. But this is, again, a positive number. That means g of delta 1 has to be smaller than 0. But this is a contradiction. We were saying delta 1 is greater than delta b, and just by inspecting this polynomial, g is greater than 0 for that. So we arrived at a contradiction. And this is our desired contradiction, because now we can conclude the first excited state in any two-dimensional CFT who has an operator that satisfies the c equals the 16 delta O cannot have the first excited state greater than delta 1. It has to be smaller than 1. So this was kind of maybe a little too technical, but if you have questions at this point, I'm happy to answer before moving on. Cool. So I'm gonna try to wrap up, and I'm just gonna tell you what happens if you keep adding more and more terms from the expansion. The crossing equations get updated like this. The key point here is these A2Ks are the pillar coefficient expansions, which are all positive. So you always end up with something. You always end up adding something positive to something positive. So the 0 gets shifted leftwards a little bit, and you define new functions and look at their new zeros, which are slightly shifted. And okay, I'm gonna just get to the end. And what I'm trying to show you here is, as you keep adding more and more terms from the Virasoro block expansion, the bound it keeps getting better and better. So our initial truncation, assuming our initial truncation just justified by saying, oh, the next term is actually small because it's suppressed by -2 pi, it was actually a consistent truncation, because if you add that small thing, that the bound doesn't only stay intact, but it gets better. So this lets us conclude that there exists an infinite number of bounds which keep getting better and better and better as you keep adding more and more terms. So the thing is, since, as I was saying, you don't know the Virasoro block in closed form, you cannot actually write this function whose zeros we're interested in fully, but you can just compute more and more and more terms and keep getting better and better and better bounds. So that is the crux of my talk. So this was all for the special case, c equals to 16 delta O. For the general case, the algebra is more tedious, but the steps and conclusions are the same. you define these new guys here, and again, I'm gonna flash the general result. Just I'll read it in words. So in an arbitrary two-dimensional CFT with central charge C greater than 1, given a scalar with a subparameter O with dimension delta O, which was our external operator, the lowest dimension non-vacuum Virasoro parameter O1 it couples to, which can be actually spinning or scalar, has its dimension bounded above like this. So that is the result. And we can actually see this at work. Just like pick some arbitrary C. I just randomly picked this number 11.5 and external dimension set to 4.9, and we see this gamma function is positive above this guy. So the first excited state has to be somewhere here. So this gives us the bound. The first term in the expansion gives us the bound as 13.5. If we go to the next term, as I was promising to you, the bound gets better. It becomes from 13.5 to 30.2. And if we keep adding more and more terms, it keeps getting better and better. And that shows that it's intactness. If you try this with your minimal models, this is actually not valid to do it, because for the minimal model values, these coefficients, pillow block expansion coefficients, are not positive definite, but sometimes they're positive enough. And when that is the case, you actually get pretty nice bounds. So the known result is the first excited state in this Ising CFT with the external, the operator set to the spin operator is 1, but using this numerics, we can actually bound it to be by this 1.001. That's pretty close. Same thing with the critical Ising value and so on. And yeah, before finishing, I'll just say, usually, I mean, holographers are interested in the large central charge limit because that gives us a gravity dual in the bulk in ADS. The bound in the large C limit looks like this, but it is trivially satisfied if you have like a single trace operator, in your CFT in the bulk that corresponds to a Lagrangian field, but it will the bound actually you derive from this algorithm is trivially satisfied by multi-traces of your single trace, which just correspond to multi-particle states in the bulk. So we don't get anything non-trivial in the central, large central charge limit. That was all. Thank you.
Thank you so much, Bert, for this beautiful talk. Let's see. Are there any questions from the audience? I'm trying to check the chat as well. Okay, seems like we don't have any questions. And then I'm going to stop the recording.